In this video, we're going to think about how we can obtain the discount rate that I've talked about in previous videos. So there are two main elements that we want to account for when we're thinking about discounting the cash flows of a project. The first is the pure time value of money. That is, dollars obtained in the future are worth less than dollars that we can get today. We want to convert money from the future into money today, but we need to know by how much we need to adjust. So I want to put that into this bucket of pure time value of money. In addition, we want to account for the fact that riskier cash flows are worth less than safe ones. If I tell you that I can give you $100, or I can give you $200 with a 50% probability, or $0 with a 50% probability, most people, most humans in fact, prefer $100 for sure than a bet that gives them in expectation $100, but has risk. So we want to know by how much we need to adjust cash flows because of the fact that they are risky. So let's start by the pure time value of money. Really, the element of the discount rate that adjusts for time value of money is really what we call the risk-free rate. And this is usually the interest rate that is paid annually by the government for an equivalent time period to the project that we are looking at. A very common choice is to use the government's 10-year constant maturity interest rate. So what does that mean? If I have a project that lasts for 20 years, on average, I'm going to be waiting 10 years to receive those cash flows. And that's the intuition for us using the US government's 10-year rates. So the idea here is, how much do investors require in order to wait to receive their money? Well, we can look at an application where people are doing exactly that. When you lend to the US government, you are not really thinking about whether the US government is going to pay you back that money. And that is the sense in which we call it the risk-free rate. There is no credit risk with the US government. And so we can look at how much the US government is paying investors when it borrows. Because in those kinds of applications, that is exactly what investors are doing. They are trading off dollars today for dollars sometime in the future with no risk that they're not going to be paid back. Again, we usually look for the US government's 10-year yields or 10-year rates as a place to obtain the cost of waiting. I will return to this in a couple of slides. The other element, as I said, that goes into obtaining a discount rate is risk. Now, in finance, we think about risk in a very specific way. And in particular, we never include in our discount rates any risk that we can get rid of. We call that risk idiosyncratic or diversifiable risk. Now, how do you get rid of risk? You get rid of risk by placing many small bets as opposed to placing one large bet, or as people often call this, you assume that investors are not putting all of their eggs into just one basket. By having investors buy a piece of several firms, they can get rid of any risk that is specific to an individual firm, and they will be subject to only market risk or systematic risk that I will turn to next. Now you might say, well, but as an entrepreneur, if I hold many shares in one company, I am very subject to idiosyncratic risk. I am very subject to what will happen to that specific firm. I am not fully diversified. You would be right in thinking that. But when we are thinking about determining discount rates, we are not taking the perspective of the entrepreneur that is very exposed to her own firm. We are instead taking the perspective of the investor. And the investor has shares in this small firm, but also has shares in many other firms in the market. They may hold a diversified portfolio of firms in the S&P 500, for example. They may hold shares in several other small firms. Now, when that happens, the law of large numbers and the central limit theorem apply. And so you are likely to obtain average outcomes across all of those firms. And any risk that is specific to one individual firm goes away. Sometimes one firm is going to do well, another firm is going to do poorly. In another period, the first firm may be doing poorly, the other firm will be doing well, and that kind of risk washes out. Well, what is left then? Because I said we need to account for risk. Well, the piece that is left is what we call systematic risk. Systematic risk, you should think of it as risk that I cannot get rid of by diversifying. Now, if you think about holding, say, the most diversified portfolio you can in United States public equities, so you would go to buy firms in the New York Stock Exchange, in the NASDAQ, and a variety of other markets, it will still be the case that the market sometimes goes up and sometimes goes down. And you cannot really get rid of the fact that there is variation. There is still variance to what is happening in the market. I cannot get rid of that risk. The way to think about systematic risk is, how does the firm that I just bought, how does one share in the firm that I buy increase or reduce the risk of my overall portfolio if that overall portfolio is already well diversified? And as I wrote on the slide, this is measured by how the firm's returns co-vary with the market returns. And we call this the beta of a firm. Now, where does that expression beta come from? Well, it comes from the fact that the way to measure how the firm's returns co-vary with the rest of the market is by running a simple linear regression. So how do you measure this? You would measure this by having the firm returns on the y-axis and having the market returns on the x-axis, and then observing how the two, measuring the two, say day by day or week by week in the public markets, okay? So you would have something that would look like this if you were to measure, say, over 5 years monthly returns. Then you would have 60 observations of market returns. Each one of these would be a month where you would see what were the market returns in that month, what were the firm returns in that month. And you would obtain one of these observations, and you can measure this over typically 5 years with monthly returns. Now, how do you see? And over here, I'm just going to draw a line. You can fit a linear regression through these points. And the beta is the slope of this line. That's going to tell you how the firm's returns are related to the market returns. And this is the part of the risk that I cannot get rid of. Now, how do we put everything together? When we're looking at discount rates, we want to have the risk-free rate, which is this component. The risk-free rate is this component. Then I have the beta that we just discussed, and then I have the market risk premium. So let me go through each one at a time. So the discount rates, RD, that I have in this expression is made up of what? Pure time value of money, RF, shown here. Suppose this could be, say, 2%. Right now in the United States, in May of 2019, the United States is paying roughly 2.5% to 3% for 10-year loans, if you want, for borrowing at 10-year periods from investors. Then we would measure for a given firm its beta. The beta for the market by definition is 1. If you think about how the market returns are related to itself, the beta is 1. So if the beta is bigger than 1, that means that the firm is more sensitive than the average firm out there to what is happening in the market. If the beta is less than 1, that means that on average the firm is less sensitive than the average firm out there to what is happening in the market. Let's suppose that we have a firm whose beta is exactly the same as the market, 1. Then I have the market risk premium. Now, the market risk premium is a number that you measure over very long periods of time. And what this is, as is indicated by the letters, it is the average return on the market, RM, minus what is on average the risk-free rate over long periods of time. Now, this difference in the United States is somewhere on the order of 4 to about 7% if you measure it over, say, the last 8 decades. There are different choices that you could make for your market risk premium. As I said, it's going to be roughly between 4 and 7%. Let's say that I use 5% here. Then we would say that the discount rate for this firm would be RD given by 2%, the rate that the US government pays on 10-year bonds, plus the firm beta, which in this case I just said it was an average firm in the market, times a market risk premium of 5%. Any number between 4 and 7% is reasonable, which will give you inevitably a range for the correct discount rate for this firm. So if these are the inputs, then you would say that the discount rate for this firm would be 7%. The discount rate for the cash flows produced by this firm. Then you would do discounting just like we discussed in previous videos. If you have a cash flow that this firm produces in a year, you would want to take that cash flow and divide it by 1 plus 7% in order to convert it into dollars today.